In 1957, a 26-year-old graduate student at Princeton finished his PhD thesis. His name was Hugh Everett III. His advisor was John Wheeler, one of the giants of 20th century physics, the man who later coined the term black hole. The thesis was 137 pages long. It was titled The Theory of the Universal Wave Function, and it almost didn't get accepted. Not because the math was wrong. The math was fine. It got pushed back because what it implied was, to most physicists at the time, simply too much. To understand why, you have to understand the problem Everett was trying to solve. Quantum mechanics had been around for about 30 years by 1957, and physicists were stuck on one part of it that nobody could really explain. At the smallest scale of nature, electrons, photons, single particles, objects don't have fixed properties. They exist in something called superposition. A particle can be spinning two ways at once. It can be in two places at once. It's not blurry because we can't see it well. It's actually, physically, in multiple states. But the moment you measure it, the moment some external instrument records what it's doing, it snaps into one state, just one. The cat in the box is alive and dead until somebody opens the box, and then it picks. Nobody could explain why measurement did this. Not really. Niels Bohr and his circle in Copenhagen had basically agreed on a rule. When you measure a quantum system, the wave function collapses. The blur becomes a single answer. And the official position was, please don't ask why. This was called the Copenhagen interpretation, and for 3 decades, it was less a theory than a polite agreement to stop poking at the part that didn't make sense. Everett poked at it. His answer was elegant and quietly insane. What if the wave function doesn't collapse? What if every possible outcome of a quantum measurement actually happens in different branches of reality? The particle went left in one branch, the particle went right in another. Both branches are real. Both continue forward in time. The cat is alive in one universe, dead in another. And there's no fact of the matter about which one is the real one. They both are. If you take this seriously, the universe has been doing this since the beginning. Every photon hitting an electron, every radioactive atom deciding when to decay, every interaction at the quantum level. The universe splits, constantly, continuously, for 13.8 billion years. The number of parallel universes this implies isn't astronomical. It's not even a number with a regular name. It's bigger than anything physics has a casual way of describing. And in some of those branches, a version of you exists. Not a copy, not a clone. A real, physically existing version of you. Made of the same atoms, descended from the same history, separated from you by a quantum event that broke one way for you and another way for them. Most of those splits happened so long ago that the people in those branches aren't really you anymore. They're very distant cousins. But the recent ones? The branches that split off a few months or years ago? Those people are still recognizably you. They live in a place that looks a lot like where you live. They have most of the same memories. And then one of them did something you didn't. When Everett submitted this thesis, the physics community mostly ignored it. The people who didn't ignore it were openly dismissive. The version that finally got published was watered down. Wheeler had asked Everett to cut the most provocative claims and soften the language, and Everett had reluctantly done it. Even the softer version sank without a trace. In 1959, Wheeler arranged a meeting between Everett and Bohr in Copenhagen. The plan was for Everett to make his case in person to the most influential physicist alive. By every account that survives, the meeting was a disaster. Bohr essentially refused to engage with him, treated him by one description like a student who hadn't done the reading. Everett came back to America shattered. He left academia entirely. He never published in physics again. He went to work for the Pentagon's Weapons Systems Evaluation Group, doing classified game theory research on nuclear war strategy. He developed mathematical models for thermonuclear exchange. He helped shape American nuclear doctrine in the 1960s. He smoked constantly. He drank heavily. He put on weight. He kept his theory in a drawer. And then in 1982, at the age of 51, he had a heart attack and died in his bed. He never knew that within 20 years of his death, his interpretation would be taken seriously by some of the most respected physicists alive. Stephen Hawking would flatly call many worlds trivially true. David Deutsch at Oxford would build his entire career defending it. Sean Carroll at Caltech would write a major book in 2019 arguing that it's the simplest, cleanest interpretation of quantum mechanics and that physics should embrace it. In 1970, a physicist named Bryce DeWitt published an article in Physics Today that gave Everett's theory the name everyone uses now: many worlds. That article is what slowly, eventually, dragged the idea into the mainstream. Everett missed all of that. He died in this universe, thinking he'd wasted his shot. Many worlds isn't the only way physics ends up with the multiverse. It's the most personal one, the one with branching timelines and alternate versions of your specific life. But there are other roads to the same conclusion, and they're worth understanding because they show how multiple, completely independent lines of reasoning all keep landing in the same strange territory. The first one is almost too simple. It's just about how big space is. The universe we can see, what astronomers call the observable universe, is limited by the speed of light. We can only see light that's had 13.8 billion years to reach us. Anything beyond that horizon is, for us, invisible. The light hasn't gotten here yet. But space itself doesn't stop at the edge of the observable universe. As far as we can tell from inflation models, space keeps going. Possibly forever. Possibly close to it. If space is infinite, or even just absurdly large, something mathematically inevitable happens. The number of ways you can arrange a finite amount of matter in a finite volume is also finite. There's a limit. So if space contains infinitely many regions the size of our observable universe, the arrangements of matter have to repeat. Somewhere out there, unreachably far away, there's a region of space where the atoms are arranged in exactly the same pattern as they are here. The same galaxy, the same Earth, the same room you're sitting in, the same you. Not a parallel universe in another dimension, just a perfect copy, sitting in regular space, separated from you by a distance so large that the observable universe wouldn't even register as a rounding error. This isn't speculation, really. It's just what happens if space is big enough. Max Tegmark, the MIT cosmologist, has done the math on how far away your nearest perfect copy is. The number he gets is in the range of 10 to the 10 to the 28 meters. Don't try to picture that. Nobody can. The second road is stranger. It's called eternal inflation. In the late 1970s and early 1980s, physicists like Alan Guth at MIT and Andre Linde at Stanford developed the theory of cosmic inflation, the idea that in the first tiny fraction of a second after the Big Bang, space expanded at a rate that's almost impossible to describe in normal terms. Inflation explains a lot of things about our universe that otherwise wouldn't make sense. But here's the part Linde figured out. Once inflation starts in a region of space, it doesn't necessarily stop everywhere. Inflation can keep going forever in some places, only ending in localized pockets that fall out of the inflationary state and become slow-expanding universes like ours. If that's right, and a lot of physicists think some version of it has to be right, then our universe is one bubble in an eternally inflating sea. Other bubbles formed before ours and are still forming, in regions of space we can never reach. Each one is its own universe. And here's the kicker. When a bubble forms, the laws of physics inside it can be slightly different from the laws inside ours. Different values for the fundamental constants, different rules, different possibilities. In some bubbles, the constants are close enough to ours that stars and chemistry and maybe life could work. In others, the laws are so different that atoms can't form at all. Empty, dark universes, lifeless from the moment they began. You can't reach these bubbles. Light isn't fast enough. They're not part of our universe in any operational sense. But if eternal inflation is the right way to read the cosmological data, and right now it's our best model, they're out there. And there's one detail in eternal inflation that gets physicists genuinely excited. If two bubble universes ever collided in the distant past, their collision might have left a faint, detectable imprint in the cosmic microwave background, the ancient light left over from the Big Bang, a circular bruise in the sky. In 2010, a group of cosmologists, led by Stephen Feeney, went looking for those bruises in the data. They found 4 candidate signals. The evidence is contested. None of it is conclusive. But people are still looking. We might eventually see the place where our universe touched another one. Hugh Everett had a son. His name is Mark Oliver Everett. He's a musician, fronts a band called Eels, and he barely knew his father. By his own account, growing up with Hugh was like sharing a house with a stranger. The man worked constantly, drank heavily, smoked 4 packs a day. Hugh died in 1982. Mark was 19. He didn't even know back then that his father had been one of the more quietly important physicists of the 20th century. He found out years later. A BBC documentary crew contacted him, wanted his perspective on his father's theory, and Mark agreed mostly because he had no idea what he was agreeing to. The film ended up becoming something else along the way. Mark traveling around the world, sitting with the physicists who'd inherited his father's work, trying to reconstruct a man he'd lived with for 19 years and never actually met. There's a scene in it where Mark asks one of Hugh's Princeton colleagues what his father was like. The physicist takes a long moment, then says, "He was brilliant, and he was lonely. He believed in his theory completely, but by the end he'd made some kind of peace with being ignored." Mark just nods, doesn't say anything for a long time. For the Everett family, Many Worlds was never just physics. The years after Hugh's death were difficult. There was more loss, and the theory Hugh had built started to feel less like a scientific argument and more like a doorway. Mark eventually walked through it, made the film, met the man on the other side of his father's work. In this universe, he and Hugh never reached each other. In another one, by Hugh's own theory, maybe they did. Here's the question that always shows up, eventually, in any honest conversation about many worlds. If every version of your life is real, if there's a branch out there where you made the right choice, married the right person, took the right job, said the thing you didn't say, does this version still matter? This is the philosophical trapdoor underneath the entire theory. Once you fall through it, it's hard to climb back out. You didn't fail, you succeeded somewhere. You didn't lose them, you kept them somewhere. Every tragedy you've lived through has a universe where it didn't happen. Every regret has a version where you got it right. The grief, the hope, the effort, all of it is happening anyway, just in branches you can't reach. If everything happens, what does it mean to try? Philosophers have a name for this. They call it the trivialization problem, and it's been the most serious philosophical objection to many worlds for years. If every outcome is equally real, then the concept of moral significance starts to look strange. Why be honest if there's a branch where you lied and it worked out fine? Why work hard when there's a version of you who didn't have to? Why love this specific person when there's a branch where you love someone else just as much? The answer most physicists give is unsatisfying, and I'll tell you up front that I think it's the right one anyway. David Deutsch at Oxford has been making this argument for 30 years. He says, the existence of other branches doesn't reduce the significance of this one, it increases it. Because whatever you do here, you do as a representative of yourself. Your choices shape which branch you inhabit, and the branch you inhabit is the only one you'll ever experience. From the inside, this is the only universe there is. The other versions are real, but they're not you. You are this version, walking this path, with these memories, with these people. That's not nothing. That might be everything. And then there's the question of free will, which the multiverse makes weirder than it already was. If the universe is branching at every quantum event, in what sense are you choosing anything? The branch where you make the other decision exists already. The branch where you said yes instead of no, stayed instead of left, called instead of stayed silent, those branches are out there, equally real, equally physical, equally peopled by versions of you living different lives. So when you deliberate, when you sit with a decision, when you feel the weight of trying to make the right call, what exactly is happening? You're not selecting which reality exists. You're selecting which version of yourself is the one looking out through these eyes right now. Maybe that's a choice. Maybe it isn't. I honestly don't know. The physicists I trust on this don't agree with each other. But I'll tell you what I think, for whatever it's worth. Think about the person you love most in the world. Then think about the fact that in most branches of the multiverse, you never met them. Some quantum event somewhere in your shared history broke a different way, and your paths just never crossed. The relationship that anchors your life doesn't exist in the overwhelming majority of parallel universes, but it exists in this one. That's what I keep coming back to. The multiverse doesn't make this universe less precious. If anything, it makes it stranger and more particular. Out of every possible way reality could have branched, you landed here, with the specific person you love, with the specific friends you have, with the specific memories you carry around like a small private collection nobody else in any branch has in the exact same combination. That didn't have to happen. Almost none of the branches contain exactly this. You are, in a weird and specific sense, cosmically unlikely. which is just another way of saying, you are not generic. This life is not generic. The version of it you're living right now is not interchangeable with the others, even if the others are real. And then there's Hugh Everett. In this universe, he died alone, drinking, estranged from his children, unrecognized by the community he had tried to convince. That's the branch we're in. That happened. We have to sit with it. But his son went looking. Years later, when Hugh was already gone, Mark made the documentary, sat with the physicists, learned who his father had actually been. And in the process, he found something his father hadn't been able to give him while he was alive, which was a way of understanding him. Hugh Everett gave the world a physics in which nothing is ever fully lost, in which every version of every choice keeps existing somewhere, in which the father and son who never reached each other in this universe might, in some sense, have made it in another one. I don't know if Hugh Everett would have been comforted by what his son did with his work. He didn't get to find out. I want to be clear about something before we end. The multiverse is not a proven fact. It's a family of hypotheses, all of them derived from our best physical theories, none of them currently testable in any direct way. We are sitting at the edge of what science can verify, looking out into a place that might contain everything we've ever hoped for, or might just be a misreading of the math. I don't know which it is. Neither does anyone else. But here's what I'll say. The version of you in another universe, the one who made the other choice, they're doing whatever they're doing. You can't reach them. You can't trade places. You can't even know if their life turned out better than yours. What you have is this branch, this version, this specific, improbable, unrepeatable thread of reality that brought you here, to this moment, hearing these words. And the question that actually matters isn't what they're doing. It's what you're going to do next. The universe has been branching since the beginning of time. It'll keep branching long after we're gone. Infinite versions of infinite lives spreading out through infinite space. And in all of them, right now, there's a version of this exact moment. Someone choosing. Make this one count.